University of Massachusetts at Amherst, Chemical Engineering, Polymer Science, 757, Polymer Rheology, H.H. Winter, Lecture 17A. Gels are known to be very soft materials. You can break them very easily. So they have very good properties as adhesives or damping materials, but they wouldn't be sturdy enough for many applications. So we wondered how we could increase the strength of the gels. And you could write down an equation for the gel. This would be, say, for the modulus of the gel would be G of T is equal to some fun factor, let's call that capital S, the strength of the gel, to the T to the minus N. That would be the relaxation behavior. And we would like to increase the value of the fun factor to make the material mechanically stronger. So that's the objective. And we try to do that by introducing entanglements, by using precursors which have a very high molecular weight. There are several ways of doing that. We could, for instance, use end-linking polymers. There would be long linear chains with functional ends, and make those long linear chains just long enough. Make them with a molecular weight above the entanglement molecular weight, and then we'll get some tough gels. However, there's a limitation, a natural limitation in doing that. If you go to higher and higher molecular weight, then the concentration of reactive ends per unit volume is going down and down. So above a certain critical molecular weight, the reaction will not go to completion, and you might not even be able to reach a gel point because of that limitation. We used a different approach. We took molecules which were very long and had functional groups along the backbone. So along the chain, if this would be two chains, is possible to form connectors, and those chains would be, of course, flexible molecules. So we are forming a network which has strands given by the distance of those functional ends along the backbone, and they are automatically connected because of the long chains. Now, this approach has another advantage. For those long linear chains, we know the relaxation spectrum already. We know that H as a function of lambda is given by the self-similar behavior cut off at the longest relaxation time, and then at short times, you know, a glass transition comes in. So initially, we know those materials will have a BSW spectrum. And when cross-linking this material, we know that somehow at the gel point, they will have a spectrum which is something like this, is a power law spectrum. Certainly when cross-linking the material, the longest relaxation time will be increased, so somehow we will combine this spectrum with a transition here with a divergence for the longest relaxation time. So that's what we would expect. We don't know what the slope is of this curve. We don't know the intermediate behavior. We know that at short times in here, the material will behave like a glass before, because liquids and solids all behave glassy at very high frequency or at very, very short time. So there will be no difference. But the question is, what's happening in the center, and how does cross-linking put all of this together? The material we used was a polybutadiene. It's a long linear chain which can be produced with uniform molecular weight. One can make nearly monodispersed samples with that. And here's a list of our 4 samples, molecular weights of 20,000, 44, 97, and 200. So the entanglement molecular weight is about 2,000 or 3,000. We have already 20 times the entanglement molecular weight for the shortest molecules I'm listing there. So we have entanglements in all cases coming up. Another advantage of the system is the chemical reaction. The side chains here are vinyl groups, which we could connect as before with the PDMS samples using the silane reaction. So we will use a crosslinker which has an SRH group here to connect into this. And we can use all the information which is available on the silane reaction, which is enormous. Also, we can easily measure the extent of reaction because we learned how to do that with PDMS samples. Aranguren and Markowsko proposed this type of specific crosslinker for the reaction. So this came just handy for us. And again, we can stop the reaction by poisoning the catalyst with sulfur or with another catalyst poison. And we can use the Pompeii method to get those stopped samples and test them extensively for a variety of cases. Okay, so that's the test system. And by having a well-defined initial condition and a well-defined definition at the gel point for the rheology, for the rheology is well-defined, we can expect that the experiment will give us some pattern, will be easy to analyze because everything is so well-defined. You saw already the initial condition. This is the spectrum, G prime, G double prime, of the initial set of samples. Here, the different 20,000 molecular weight is the shortest one here. It has a characteristic time of about 10 to the 3 already. Actually, frequency here, 10 to the 3. And the spectrum here for this system is given here, the continuous spectrum, the BSW spectrum. And the data are described very nicely with this spectrum. This spectrum is represented by the line here going through the data. So we will do experiments with the shortest sample. It has some entanglements, as you can see. And here you can see the longest relaxation time is about 10 to the minus 3 seconds in that order. Just the reverse of the as shown above. The data were measured at a variety of temperatures using the time temperature superposition to increase the window for the experiment. Now, when performing cross-linking reactions, we will change the speed of reaction and we will not be able to perform time temperature superposition. Only on stopped samples we can do that. Now, this is a typical evolution of the sample with 20,000 molecular weight. It has about 8% of vinyl groups along the chain. And when you count, in this case, it's a chain which has about 30 reactive groups along its backbone. So functionality would be 30 in this case. The initial spectrum for G prime and for G double prime is shown again here. And then with increasing extent of reaction, the modulus increases. The longest relaxation time is increasing, so the terminal zone moves to lower frequencies. And then there's an intermediate state, a power state. Before that, the material is still a sol. Beyond that, it's a gel. There's some structure in the data which I should discuss. Here, the solvent effect is seen. To have a stoichiometric ratio of 1, about 20% in volume comes from the crosslinker. And the crosslinker is this very small molecule. So this is acting like a solvent when you look at the system rheologically. It's mobilizing the molecules. So the solvent contribution reduces the modulus somehow. And then as the reaction proceeds, those little molecules are connected to the backbones, and the modulus is increasing like that. So this changing here is nothing else than the reduction of the solvent effect with cross-linking. But somehow the general feature of the behavior in the entanglement region doesn't seem to be changed by the introduction of cross-links. Here for G double prime, you see also the effect of solvents. A solvent basically reduces the spectrum, puts it further down, and changes the characteristic time to a shorter value, to a higher frequency in this case. Here for G double prime, it's harder to identify where the gel point is. 10 delta is even more critical for the sol-gel transition. We would expect a constant 10 delta in the terminal zone. 10 delta should be flat here. And before the gel point, the material at low frequency, at long times, should act like a fluid. 10 delta will go up. And beyond the gel point, it goes down. And the gel point occurs at a conversion of about 20%. And later on, we will talk about this. Theory of Flory and Stockmeyer predicts about 20% conversion if you crosslink a system which has a functionality of 30. Okay, so that's pretty consistent. And again, you see the terminal zone adopting this power law behavior. This region is known from the entanglement behavior. See, it goes down with a slope of minus n about, and this is the transition to the glass at very high frequencies. The gel point can be determined very accurately by taking data, so-called frequency sweeps. Let's take the first data set here. See, every data point is taken at a different time. We're plotting 10 delta versus time. So we're taking one frequency after the other, and a new material is being probed. And important, when doing that, it's important that the cross-linking reaction doesn't go too fast. And this goes something like this. If you have a quantity which you want to measure, which is changing during the periodic experiment, something like this, and the duration of such a periodic experiment would be, 2 pi over omega. This would be a characteristic experimental time for probing the material. Now, the quantity which we want to measure, maybe some modulus, is changing in time. This would be the rate of change of the modulus at the time we are performing this experiment. And if we take now the relative change of this quantity, we divide it by the instantaneous value of that. Okay? So that's the relative rate of change of the quantity which we are measuring. It could be G prime or G or whatever. G is just symbolic for the experimental quantity. That's the rate of change. And we multiply this now with the experimental time. And the experimental time is 2 pi over omega. That's how long we need in order of magnitude for performing this experiment. So this is the rate of change multiplied with the time. This will give us the total change of our property during the experiment. And if this total change is smaller than 10%, if it's 10% is kind of the limit. So if we say if this is smaller than 0.1, then our experiment is okay. And that's what we are doing. We are slowing the reaction down, and as we measure a property which changes rapidly, we go to higher and higher frequencies. Or vice versa, you can see that in a sample which is cross-linking over with time, you can never probe the material at very, very low frequencies. You're limited in your range because of this criterion. This number here, by the way, we call this the mutation number. And say if this mutation number is smaller than 0.1, then our experiment is okay. Then we can do time-resolved rheometry. And people in spectroscopy do the same thing. They do time-resolved spectroscopy, and instead of G, they would use another property. So that's quite common. So this is what we are doing in our experiment here. We get our data points, and we are far below this limit. And so data are okay. And we have a software analyzing data. We call this Gel Pro. We just put those frequency sweeps in there and process the data. So this gives us a gel point by just putting lines through the points, and the crossover is here at the gel point. The spectrum for this material is drawn here. The initial spectrum is described by the glass transition, and then in the scale here, everything is pushed together with many frequencies. This is the entanglement regime, and then the longest relaxation times are increasing. And at the gel point, it turns out that all the slopes we are finding so far are close to 0.5. I would be hesitant to say that this is a universal material quantity, because all the other exponents are changing between all kinds of values. But for all our vulcanizing systems, we find a slope of 0.5 and this we would describe with the gel equation. This would be the lower limit where entanglement is setting in. We would maybe use a BSW equation for this part, and the gel, the Chambon type spectrum in this range. Now, the continuous spectra which are drawn here can be approximated by a discrete set of many, many Maxwell modes. And with those Maxwell modes, you can solve equations very easily. You could, for instance, calculate now G prime, G double prime, and compare the prediction with the data. These are the data at the gel point. You see the entanglement regime, and then you see the power law region going to lower and lower frequencies. We don't know about the sample beyond the experimental window, but it's certainly the feature which we would expect for gelation, terminal zone being power law. This is the entanglements. And the tough gel properties now, the increased front factor comes in by changing G prime instead of going in. You see, before, with low molecular weight materials, we would come from the glassy regime and would continue here. And now we are lifting this up with molecular weight. And if we would go to higher molecular weights, we would lift it even further. So tough gels would be characterized by this type of procedure. The initial spectrum shows, let's say the spectrum of a low molecular weight material shows a glassy region, and then it shows the typical Chambon spectrum. And now with entanglements, we raise this, we have entanglements effect, and then again we have the same terminal zone. And this gives us the high front factor. And I think that has a nice potential for tailoring properties of adhesives and damping materials. It's a new approach. I don't think anybody has looked at that. Now, experimentally, it becomes a problem to go to higher and higher molecular weight. We will not be able to measure the gel point of, say, polybutadiene at 200,000 molecular weight. And this is shown here. At the reference temperature, close to room temperature, the spectra of our 4 samples are shown here. And this is our experimental window, the frequency window, at our near room temperature. So in this window, we only see the entanglement regime of the 200,000 molecular weight. And this entanglement regime is not altered very much by the crosslinks which are coming in. It's only the terminal zone which is altered, and the terminal zone which will go into this power law behavior will happen outside our experimental procedure. So we couldn't stay in this window and look, for instance, for 10 delta being independent of frequency. We would not detect anything specific when the material goes through the gel point. And that's a serious problem. Let me show you some data measured by Mike DeRosa. This is the sample here of 44,000 molecular weight. It's a fairly high molecular weight sample. And I drew this is 10 delta as a function of reaction time. And I drew some tangents in here, and a clear distinction is made where the gel point occurs. However, if we go to the 97,000 molecular weight, you can see 10 delta within our frequency range. These are different data taken at different frequencies as a function of time, and they never cross. So people might just look at this fingerprint here and say, oh, you wouldn't see self-similar behavior at the gel point. Look at this here, it never occurs. It does occur, but outside the experimental range. It's very, very difficult to decide on new experiments which would tell us the gel point of those highly entangled materials. We couldn't go to higher temperatures because that would change our reaction speed, would change everything. So there might be a limitation in temperature also. There was a study in industry where they looked at a material which has a high molecular weight and had the tendency to crosslink very early. Now, exactly that pattern of relaxation developed in that system. So in that case, the rheometer could only pick up the limit, could just barely pick up the gelation problem. But if they go to higher molecular weights in their sample, they would have to use other techniques to see what's happening. In this case, they tried to avoid the cross-linking material. So they monitored the development of crosslinks to slow that process in eventually. Let's move to another subject. The temperature dependence of the response near the gel point. The linear viscoelastic behavior follows time temperature superposition as long as there is no transition, say, of a glassy material coming in, or crystallization, or phase separation changing the material. So any of those transitions would alter the behavior. But the transition through the gel point is very gradual. And we would expect that time temperature superposition holds. And indeed, we tried that. We applied this in many cases. We looked at gels at different temperatures. Here we have G prime, G double prime at 2 temperatures shown. A shift of those curves into this set, shifting into that set, would not alter the slope. Okay, so I loosely drew this. This is a little steeper than that. Just to make the point very explicitly. If time temperature superposition is valid for our system, we found that experimentally, then this slope has to be exactly equal, to that slope. Okay? So we are just shifting into each other. And we will get a master curve of this type. And Chambon has done that initially in '85. That's how he got 5 orders of in frequency for his data. So he will get a master curve. There's a problem already with the shifting. See, the self-similarity of that spectrum doesn't tell us whether we should just shift over or whether we should just shift up. In all cases, we will achieve our shifting. So there's some ambiguity in that. And certainly shifting works. That's what we always see. But we cannot come to a conclusive answer saying that whether the shift factor AT of the maybe viscosity of the initial material and BT shift factor of the modulus of the fully cross-linked sample, whether those are also the shift factors of the critical gel, the material at the gel point. We looked at materials which were very far away from TG. So I would say as long as we stay away from TG, those shift factors are not affected. But if you have a system where TG increases drastically with the cross-linking reaction, and you move closer and closer to TG, then you're somewhere else on the WF curve, and you certainly will have new behavior coming in. So for our systems, we made sure that we were far away from TG. Akihiro Iizuka studied that same problem here. He looked at his caprolactone gels, long linear chains with 3 functional crosslinker, at several different temperatures. You saw this table before. He took only the 4 higher molecular weight samples. The lowest molecular weight sample didn't give enough stress response. This molecular weight was too low, and then when he went to high temperatures, he just couldn't measure anything anymore. So that's why he excluded that. And the precursor viscosity followed an Arrhenius relation. He got the shift factor here. This is the precursor viscosity for the 4 samples here as a function of 1 over temperature. So you can see the linear Arrhenius plots. We are far away from the glass transition. And the equilibrium modulus is proportional to the temperature. And that's already a surprising result. At least I found that surprising, because we know that the modulus goes with rho t over rho 0 t0, you know, that shift factor. But the density doesn't seem to change very much in that system, so we only have a t dependence in the modulus. And the higher the modulus, you know, it goes 1 over molecular weight. The higher the molecular weight, the lower the modulus and the lower the dependence on temperature. So at low molecular weights, you have a strong temperature dependence, which is consistent with that. And you can also see that for a set of samples which were cross-linked at different stoichiometry, this effect of stoichiometry. And again, as the modulus goes up, you see a bigger temperature dependence coming in. And here you have close to balanced stoichiometry, you have the highest modulus. Then on either sides, if you have a lower amount of crosslinker or a higher amount of crosslinker, you get lower moduli. And all of this is very consistent. In fact, we used those shift factors and shifted data near the gel point and the gel behavior was described by that very nicely. Then Aki reacted materials at different temperature. He took the 7,000 molecular weight at balanced stoichiometry and reacted it at 1, 2, 3, 4, 5 different temperatures. With increasing temperature, the reaction speed increased. You have G prime coming up very quickly and G double prime over like this. It's a continuous evolution of properties. Now, where's the gel point? How could we measure the gel point? And Aki had a very nice idea in doing that. Let me describe that to you. He took the curve for the sample reacted at 110 degrees C. There, the reaction was sufficiently slow that he could measure 10 delta at a set of different frequencies and plot the evolution of those, and then you can see the gel point is occurring at this time, right? At this time. But he also took a second set of information. He said it's occurring at a certain value of 10 delta. Forgot what this value was, but there, for his sample, a certain value of 10 delta gives the gel point. And remember the relation that 10 delta at the critical point, at the gel point, is given by n, what was it? N pi over 2. Yes, n pi over 2, right? Okay. Now, if n was the same for all temperature, so this n here is not a function of temperature. Otherwise, time temperature superposition wouldn't work. You know, this argument we had in the beginning. And hoping, now that's an assumption, hoping that the statistics of network formation is the same at low temperature and high temperature, he would produce the same critical gels at those different temperatures, then he should get the same n in all cases, and then all of those systems should have the same 10 delta, right? Independent of temperature. So 10 delta, or delta itself, is not a function of temperature. So he can use now his value, the value which he measured at 110 degrees, this 10 delta value, he could measure that to determine the gel point for all of his gels, and that's where he marked it. And note, the gel point is not coinciding with the crossover of G prime, G double prime. Because it's occurring at some other time. But with that assumption, he knew where the gel point was, and he formed then G prime, G double prime at the gel point for those different temperatures, and for different samples. Then he got S. See, this was all for the 7,000 molecular weight. He got S now at different temperatures from the set of curves which I just showed you. He repeated that for all 4 samples and got S as a function of temperature. He plotted as 1 over the temperature. And he also did it for the 7,000 molecular weight at different stoichiometry. And all of this is very self-sufficient. And he got the relation. That's the summary. You would say that S as a function of T, the front factor in the gel, is equal to S at some temperature, some reference temperature, times AT to the N divided by BT. This is the type of shift we are needing. And you can see that this relation is valid by, let me draw a new thing. You could say that S of T is given by a modulus at temperature T times a characteristic time at temperature T. But we are, well, this is then to some exponent n. Remember, that's what we saw from Scanlon's experiment. We got a characteristic shortest time and a characteristic modulus describing the behavior at the gel point. Now, this modulus is known to be equal to the modulus at some reference temperature, divided by the shift factor Bt. That's just shifting of moduli. And this characteristic relaxation time at temperature T is equal to the characteristic relaxation time at some reference temperature times At. And the whole thing is taken to the n power, and you could write down the G0 times, evaluated at the reference temperature, times lambda 0 at the reference temperature to the n power times At to the n power, and this is divided by Bt. Okay, so this is the S at the reference temperature, and this is then multiplied with a shift factor, and this is the relation which I drew down here for you. Now, Aki could use the At and Bt of the initial material, the precursor, and the Bt here of the final cross-linked material, and could shift all his data in that. So nothing specific in the temperature dependence. No surprises. It's not a transition which would hinder us applying time-temperature superposition. And that's nice. That helps doing experiments near the gel point. Another subject which I want to touch just very quickly is the following. We always would like to know the conversion which is giving us the gel point, the extent of reaction at the gel point, PC. The theory of Flory and Stockmeyer is predicting that type of conversion. And if you take a material which has just multifunctional chains, let's say it has here in this first part here, you have just long linear chains which are able to react. Now, if you have chains like that, they would just form very long linear molecules. They would never form crosslinks. So you need many molecules which are able to connect on the ends, but they are at least three functional. And if you have a system which is, for instance, three functional, let's take this equation of Flory and Stockmeyer. There you would have a conversion which is equal to 1 over F minus 1. And in the case of F being equal to 3, you would have PC being equal to 1/2, right? So 0.5 is the critical conversion in this case. So this is one type of system. Now, if you have a system which has two species of molecules reacting, here we would have, say, a two-functional molecule with the functionality F. You have a two-functional molecule, which is probably very long, with a functionality F, and a multifunctional molecule with the functionality G. Or let's maybe make some cups here. They are able to react with those spheres here. So in this case, F is equal to 2, and G would be equal to 3. Now, in the model tells us that the critical conversion in the case of a stoichiometrically balanced system is just 1 over, what was this, F minus 1 times G minus 1 to the 1/2 power. Coming back to the sample of De Rosa, where, say, F was 2 and G was 30 about, the tough gels, which have lots of reactive ends, not just 3 reactive ends, many of those, then the conversion for a system with a balanced stoichiometry, the conversion at the gel point would be 1 over 1 times 29, and if you evaluate, the root of that, and if you evaluate this, it's about 19%. It's 0.19. And that's about what we are finding in those experiments. It's not really a proof that this theory is correct. It just means there's an agreement between there are strong believers of that type of theory and some very strong disbelievers of that theory. But somehow the magnitude of the conversion, of the critical conversion, agrees with what we see in experiments. The conversion can be measured with optical techniques. We do that with Raman, for instance. This would be now 10 delta measured at a set of different conversions. From rheology, we learn 10 delta coming in here. This is for this sample where 10 delta was equal to 1, and the conversion was close to 0.57, which in this case we would have a prediction of 0.57 having a difunctional and a trifunctional system reacting. Now there's so much about gels which are characterized by the self-similar behavior. Let me give you a few examples of materials which are also self-similar, but which are not, which we couldn't characterize as gels. So what are other occurrences of the power law behavior? First example would be the classical Raus model. This type of spectrum is coming from first principles using Raus's theory. Now, at short times, if the time are much shorter than lambda 0, then this spectrum reduces in a power law spectrum like this. So, and the cutoff would be lambda 0. I showed you an example of that. So it really reduces to a power law behavior. In G prime, G double prime, you can show that the slope is equal to 1/2 here. When you calculate the spectrum, it has a G prime, G double prime, which is unique. All Raus models have the same spectrum if you plot them with omega times the longest relaxation time as one variable, and G prime, G double prime over G as the other variable. It's just given by the same function. And this is in the order of 1 here, and beyond that, you can see that the power law behavior is. Somehow the model looks like a gel at high frequencies at small scale. But when you look at the material at larger scale, that you realize that the chain is of finite size, and it is really a liquid behavior. Another occurrence of a power law behavior is the following. Here for broadly distributed systems, we find an intermediate region where power law occurs. Here, this is the modulus plotted here, and it looks like a straight line here for some region. That has been realized by Larsen for polyethylene melts. Now, the glass region would connect here at very short times. I didn't mention that. So, but this would be the plateau modulus then, and then a glassy region and a terminal zone. Now, you could model this type of behavior empirically with a function like here, g of t. And at short times, this behavior is reduced to the modulus. Intermediate times, this will be a power law. You know, 1 is small compared to this, and we just get power law behavior. This exponential function hasn't set up in yet, but at longer times, everything is really governed by this exponential function. So you have a power law, and which is cut off by this terminal zone. One more material of that type. We have a broadly distributed polymeric material. This is tar mixed with block copolymers and all kinds of additives. And that shows also a very self-similar region at intermediate frequencies. It's a glass transition, I think, of this material. At low frequencies, you have the entanglement behavior, and at high frequency, you see the glassy material. And again, there's a power law behavior. That type of power law is certainly not describing the material at the gel point. Well, before we break, let me just as one more example here. As a material which has a long chain with side chains here, a comb-type molecule. And again, this type of system has an intermediate frequency range, which is power law. If you go to lower frequencies, you have terminal zone, it's a liquid. If you go to higher frequencies, you have entanglements, and everything is normal. So there are materials which behave like gels at intermediate time scales. But for a material at the gel point, at a transition from liquid to solid, you would have to go through a material which has power law in the terminal zone, not just in intermediate frequencies. Let's have a short break here and then continue. I have 2 or 3 more examples of power law behavior. Rheology, H.H. Winter, Lecture 17b. There are more examples of power law behavior, and in fact, for those, we might really have a liquid-solid transition. The first example of that type I want to show you that's a block copolymer found by Bates in '84. It's actually a di-block material of sufficiently high molecular weight, which undergoes a transition at, I think, close to 90 degrees C. So he had one phase above that and 2 phases below that. Now the microphase separated structure causes some long-range connectivity in the material. So in the liquid state, one phase, the material is something like this. And as it goes into the phase-separated state, it has a power law region. In his case, it was slope of 1/2, and then G prime is equal to G double prime. So that's a power law spectrum. And in fact, his original set of data looks like this. This is the original G prime, G double prime, and then at the gel point. And both of them are shifted by 1 decade. Otherwise, this would be on top of that. So we don't know whether this is continuing. Maybe it's finite, and it will be a liquid at low frequencies. Or it is really a 3-dimensionally connected region, and this power law behavior is more than just a sol-gel transition. It's just a type of liquid-solid transition which occurs when you have a long-range connectivity developing in your materials, connectivity beyond molecular scale. Right? Now, in polymer blends, Surajmani found something similar. Actually, I should have. Could you maybe reduce that a little bit? Yeah, I didn't. It's too big. So we took a blend of polystyrene and polyvinyl methyl ether. Polystyrene was, 260,000, and PVME was about 80,000 molecular weight, and fairly broadly distributed, 1.5 or so MW over Mn. And then versus temperature, here I'll show you this in parts. This is the amount of polystyrene going from 0 to 100%. The glass transition, and this is the temperature going up. Here we draw a glass transition temperature, which is here -30. It's about 100 degrees. It shows like this. And our phase separation temperature. If you go to higher temperatures here, then the material goes from 1 phase to 2 phase. And the question is, what happens to rheology when we phase separate the material? At 20% polystyrene, starting with 90 degrees, Surajmani moved up in temperature and got a phase-separated system here. Or for the 40% polystyrene, he moved up to 115 and 140 degrees. And so what's the consequence on the spectrum in this case? Here we have the spectrum of the one-phase material first, and in comparison, the power law behavior of the material when it goes two-phase. This is the 20% polystyrene sample. Becky, if you please could show that. Yeah. And then there's a sample for the here, the 40-60%. Again, this is the one-phase material, and the power law behavior is coming in. Again, we don't know how it will continue, whether it will continue to much lower frequencies, where there's really a three-dimensional connectivity. So it might be really the fingerprint of a material which is connected in large scale. Now comes the puzzle. Antonietti in Mainz in Celesco produced so-called microgels. They took long linear chains and cross-linked them into little rubber balls. Actually, I don't know whether I gave you those. Somewhere you have pictures like that. So you can take a long linear molecule, or you can take a branched molecules, or you can take a microgel where a single molecule is cross-linked into itself. And it only could touch another molecule. It could really not penetrate a neighboring molecules. It's produced in solution, for instance, very dilute solution when you cross-link a molecule. There. And in comparison, a network would stretch over the entire sample, would be the same as this, but in macro scale, where this has a finite size. Here's the chemistry described. It's basically, many cases, it was a polystyrene molecule. Now this was a different. No, I think this is a polystyrene also, which he cross-links. Now he gave us a few samples, and Yigang Lin looked at their properties. Now this is a somewhat bigger in size if you change the scale. Yigang Lin measured G prime, G double prime at low frequencies. Is typical power law behavior of that material. Typically, I mean, we saw that before. We knew that it has this behavior. We would not have predicted that the microgel has this behavior. It consists of a system without solvent, just those little rubber balls next to each other. And then at some finite modulus, there's a transition to the glass, and the slope changes here. So it's a little bit higher. So it's a power law behavior for the terminal zone. Probably might continue. I don't know. We really don't know why this behavior occurs. Wait a minute. We have now G prime, G double prime is going in a, yeah, you saw G prime, G double prime in a power law. This is the modulus now, the relaxation modulus, again following a power law. And Yigang also did creep experiments of the same system. And this also follows a power law. And the dotted line comes out of modeling calculations. You know, when just taking one value for S for the form factor, one value for N, and then all the data are consistent. We can check between creep, startup of shear or dynamic shear or the relaxation modulus, and all of this fits very nicely. Those microgels behave like a material at the gel point. And if we would know why, we would know quite a bit about molecular dynamics. Something for you to solve. You know, some puzzles are left over. Okay. So in summary, there are other materials which follow this power law behavior. And we have to be careful to not to overly conclude when we have a power law behavior somewhere in an experiment. We should know about the molecular structure to draw further conclusions. Let me do some calculations now using this equation here, using the spectrum of the material at the gel point. And this goes something like this. We would do linear viscoelastic modeling. And the starting position for the linear viscoelastic modeling will be the Boltzmann equation as we did before. And in this case, the stress in the material is given by the relaxation modulus of this material evaluated at some time in the distance from the current time, multiplied with the weight of deformation tensor at the instantaneous, or at some time, instantaneous time t prime, and t prime is going from minus infinity to the current time t. And the rate of deformation tensor is a tensor, gives us the deformation. Now we could use that for all kinds of calculations, but let me move a little further. Well, the first step would be to introduce this spectrum here into this equation, and we would now have something like what we call the gel equation. And this is given by the stress being equal to, now S is just a constant, we can pull this out, is a front factor, S times the integral from minus infinity to the current time t of this power law of the time dependence. This is t minus t prime to the minus n times the rate of deformation tensor. This is what we use for our modeling. Now, to extend this to larger deformations, this is just for linear viscoelastic modeling, we have to do something. You know that the strain tensor here, or the rate of strain tensor, is only usable for very small deformations. If we want to go to larger deformations, we could, for instance, introduce the finger strain tensor to describe this rate of deformation. And we would replace this here with the time derivative of the finger strain tensor between t prime and t. Okay, so this whole expression will be reduced. And then we have the gel equation applicable to larger deformations. Actually, when you introduce that, you can already integrate by parts. You could integrate this and differentiate this. So by doing that, you get t minus t prime to the minus n times the finger strain tensor evaluated here between t prime and t. And this is now, we introduce the limits, right? We go from minus infinity to the current time t, minus, now we take the derivative of this. We have minus n times s times the integral of t minus t prime to the minus n minus 1, right? Just taking the differential of that. And then we just put in the finger strain tensor here, t prime, t prime. Okay? Now, the front term here, the first term, is equal to 0. At minus infinity, this function is relaxing to 0. So this is equal to 0. And at the other limit, if t prime is equal to t, then the finger strain tensor is equal to 0 because it's reducing to a no deformation. Well, it all reduces to 1, and then we get just an isotropic contribution there, which it doesn't contribute. So this first term is dropping out, and our final equation is something like this. The stress tensor is given as plus n, the two minus signs are canceling, times capital S times an integral from minus infinity to the current time t times t minus t prime to the minus n plus 1 times the finger strain tensor between t prime and t times dt prime. Now the choice of strain tensor was arbitrary. I just used the finger strain tensor. You could have used the Cauchy tensor. Most strain tensors in the limit, when taking the time derivative, reduce to the rate of deformation tensor. So they all reduce to this. So when we generalize, we don't really know whether we should use a finger strain tensor or Cauchy strain tensor. There are many, many different choices. So why not formulating a solution which contains the finger strain tensor and also contribution of the Cauchy strain tensor? It's just an empirical approach. It would include more options for us. So how would we do that? We would say that we don't take the whole Cauchy strain, whole finger strain tensor, but we only take a contribution here 1 minus alpha of that. And then we take alpha times the Cauchy tensor, t prime t, alpha times this, and we would just multiply this here with the whole. Okay. Now convention is even going further. In the case of a zero strain, this tensor, or the finger strain tensor, or the Cauchy tensor are reduced to 1. So if we subtract 1 from this one here, we would have a strain measure which goes to 0 in the case of zero strain. Okay, so we would draw this. Right? And we know that in the limit of no strain, this goes to minus 1. It's kind of a negative strain measure. So we would say minus 1 minus the Cauchy tensor multiplied with alpha, and that gives us the formula which we could use for modeling calculations. Okay? So here this is a tensor 1, this just a unit tensor which is coming in. So that would be an empirical equation which we can use for modeling calculations. Now, in most cases, I will not use the Cauchy contribution. I will just use the finger strain tensor. But in real cases, if you want to get serious about it, alpha could be in the order of 0.2 when looking at experimental data on the second normal stress difference in shear. Yes. Also very little information on the precise value of that quantity. So that's what we are going to do. That's what we are going to use. We will, as a first step, we will look at startup of shear flow at a constant rate. The experiment is defined as such, as a function of time. We have everything at rest, but at t equals 0, we start up the flow and then continue at a constant rate. So it's 0, and then here constant rate. The response, the shear stress response, is given by the Boltzmann equation in the beginning. Now, the first part from minus infinity to 0 has a 0 kernel because there's no rate of deformation. Rate of deformation is 0, so only we have a contribution here from the second part. And in the second part, the modulus can be replaced by the spectrum. We haven't even specified the spectrum. You know, it can come in later, put in the Chambon spectrum here. And well, we keep that in the moment, which interchange the sequence of integration, and then we can integrate this here, this exponential function, and we find that the stress is equal, the shear stress is equal to the rate of deformation, equal to the shear rate, times this integral here times 1 minus t over lambda. And here the lambda is dropping out, so we are just rewriting the whole thing and saying we can formulate now viscosity for the startup, shear stress divided by shear rate, which is here time-dependent shear stress over the constant shear rate, given by h of lambda times 1 minus this function times d lambda, and this is integrated from 0 to the longest relaxation time. Now note if the longest relaxation time is infinite, here we might get into trouble. And this comes up in the following way here in this integral. The first part is giving us the steady state contribution. And the second part is subtracting because everything is transient. So when the transition of the startup is over, this contribution is 0. In our gel, we will have a contribution here which is infinite. You know, if the steady state viscosity is infinitely large, and then this is infinite, and then we subtract something from that. So in the solution, we have to watch out for trouble like that because of this limitation, this divergence of the longest relaxation time. This might give some problems. So into this general picture, this we haven't talked about the gel so far. We will introduce now the spectrum of the gel. It's just a fun factor times lambda to the minus n. And this holds from the glass transition time up to the upper cutoff. See if we allow to be near the critical point, near the gel point, we have an upper cutoff. And then the time beyond that is characterized by a 0 spectrum. Everything is relaxed. So if we neglect this transition to the glass, and we will do that just for simplicity, you can neglect it and then get some solutions and later on introduce it and see what effect this has. So we will neglect the glass transition, and then we will calculate the transient shear behavior by now taking the equation which we had before and introducing the spectrum above. And the spectrum in this case goes from 0 to lambda max. 0, this is where we're neglecting the glass transition here by assuming power law over the whole range. And again, this is 1 minus the exponential function. The transient part is coming in here in the second. Let's look at some limiting cases. Let's look, for instance, at steady shear flow. In this case, steady shear flow of the nearly critical gel. Lambda is not infinite, so we don't have any problem of a diverging viscosity. Viscosity is still finite. Okay, so lambda max is finite in our calculation. And we just take this expression and say that time should go to infinite, should be infinitely long, much longer than lambda max. Then the transient part is vanishing, and the solution is just given by this integral, which we can evaluate and can say the viscosity is given by some constant here, some factor, times lambda max to the power 1 minus n. Now, remember, some time ago we compared the viscosity to the longest relaxation time of a material when talking about critical exponents. We can do the same thing here. We could say this viscosity here goes with the distance from the gel point with a minus s exponent. That's just the critical behavior near the gel point. And we could use the relation above here and could say omega goes proportional to lambda max to the 1 minus n. So that's what we're saying here. Therefore, we could say lambda max goes with the distance from the gel point with minus s over 1 minus n. And this exponent is the same exponent which we already derived from experimental observations some time ago, 2 lectures ago. So no difference in the result. It's consistent with the other observations. We should do the same thing for the material in the gel, beyond the gel point, and again we would get the same exponent. So this definition which I used before, this 1 over omega of the break point as a characteristic time is really giving us the same result as the analytical picture which we have here. Now what happens in the material which has a diverging longest relaxation time? That's the critical gel, and we would like to know the startup behavior in this case. We put in the spectrum, we neglect the glass transition again, so this spectrum goes from 0 to t, and by just integrating this equation as it is, we find that the viscosity, here tau over gamma 0, goes with t to the 1 minus n. Now, n is about 0.5 or somewhere between 0 and 1. So this is a positive exponent. And the evolution of the viscosity is somehow given by this type of function. And you can see that it grows and grows and grows. The rate of growth is decreasing, but it still will never level off. And this is consistent. It will give you an infinitely large viscosity. So that's what we would be expecting. An alternative way of deriving the same result. See, this is also an exercise. That's why I'm going to show the same thing in different ways. We know already what the result is. The time-dependent viscosity is defined by this integral here. The spectrum is already introduced, and the constant rate of deformation has been put outside and has been divided. So you don't see the rate of deformation here anyway. Now, this part of the integral is integrated first. We go from 0 to infinity. We talk about a critical gel. So longest time is infinite. We neglect the glass, so we start with 0. Now, this can be rearranged by introducing a quantity here. X is equal to S over lambda, and we rearrange that equation so that we find a front factor here times S. This is small s. Yeah, this is not capital S. This is time t minus t prime. Yeah, I should mark this. Small s is equal to t minus t prime in this substitution. Okay, and then we solve this integral, which is that's the gamma function. This is the gamma function of n when you look this up in tables, and you find that this is just g0 lambda to the n, lambda 0 to the n power times s to the minus n times the gamma function. And we had the gamma function out front, so the two gamma functions are canceling. And this is the result for this integral. You introduce it here, and you integrate, and you get the same result for the viscosity. Actually, I didn't here. This is 1 minus n. This is minus n, and we're integrating once. This gives us 1 minus n. Just wondered whether we got different result. Okay. If you, in another approach, if you would take this equation for the viscosity, where you have the equilibrium, where the steady state value minus the transient part, then this steady state is infinite, and the transient cannot be solved very easily. And you would have to take some limit before you can solve that. And it will not lead to an easy solution. Now, that gave us the information about the rate of information about the shear stress. How about the first normal stress difference? We will go to the equation on the blackboard. Here we will go to this equation, and for shear flow, the finger strain tensor between T prime and T has the components of 1 plus gamma square, gamma 0, gamma 1, 0, 0, 0, 0. Okay. If you recall from previous lectures, this is for shear flow. Or if you want to introduce it here in this equation with the rate of deformation tensor, d t prime of this rate of this finger strain tensor, and if you take just the 1 component, that is just 2 gamma dot, for instance. And well, you can take gamma dot 0 and put in all the components. So let's take the 1 component minus the 2,2 component and calculate the first normal stress difference. So we take the first normal stress difference, tau 1 minus tau 2 is equal to this integral where we introduce now 2 gamma dot gamma, and we replace that with the time and the rate of deformation. See, gamma is equal to gamma dot 0 times s, and gamma dot is equal to gamma dot 0 in the time range from 0 to t. And then you integrate this and get the first normal stress difference. And you find that the first normal stress difference grows with a parabola with an exponent 2 minus n, and then has a front factor like here. Now we wanted to check that. Sundar Venkataraman produced some samples near the gel point and measured the startup of the shear stress and the first normal stress difference. And you can see data here. This is a PDMS material, 10,000 molecular weight, close to the gel point. He measured this individually, but if you take the solution we had before for the shear stress and the solution for the first normal stress difference, and you just take the ratio of the two, then you can see that they just change by t to the power 1. So the ratio should be just proportional to the time t. And indeed, that's what he finds in his experiments. Here, the data are not perfect. There's a little bit of curvature. He doesn't have a sample exactly at the gel point here, but the ratio is really very close to a function which is proportional to the time t. And at some strain, say a strain of 2, the material starts breaking and everything changes. In a step strain experiment, we also can model the shear stress. Here, let me quickly move to the next experiment. Here, this is the stress being built up, the strain being built up, the responding stress is calculated. Again, we're putting in the finger strain tensor and calculate now the shear stress. And you simply integrate that function, and you find that the stress is relaxing with the relaxation modulus. And that's the result which we would be expecting. Obviously, in a step strain experiment, you get the relaxation modulus. So the stress is equal to the strain times the modulus. Or when you take the 2 minus 1 component, you see that this goes with the strain square, but the time dependence is the same, and it also goes with the relaxation modulus. So this is all very consistent. To conclude this here with 2 more figures here. This is the viscosity, which is going to infinity in the material. When you start up shear flow, the viscosity grows and grows. The stress grows to a diverging value, which is the property of a solid, really. And the relaxation is described by a modulus which decays, and in this fashion. In the modeling, I neglected the startup, finite starting time, but it doesn't really matter at long times. It decays in this fashion. So this is the relaxation in a power law in time. So the material at the gel point has this intermediate quality between liquid and solids. And there I want to mention an old paper by Heindel and Gizikos in 1972. They looked at the power law relaxation time spectrum in the terms of continuum mechanics. And they realized that somehow a material with a power law spectrum has a liquid behavior because at rest the stress relaxes to 0. That's exactly what we are seeing. And it has solid behavior because in steady shear flow the stress goes to infinity. And they just couldn't make any sense out of that. It was okay from a continuum mechanics point of view. They didn't know about any material which would behave like that, and they called it an unreal fluid. But they realized that it satisfies all conditions in continuum mechanics, but that it wouldn't have any counterpart in nature. So when Gizikos saw our results on gels, then he said, oh yeah, this is exactly what we found from continuum mechanics derivations. And it's obviously we're describing a material which is the limiting material between the liquid and the solid behavior, and that's exactly where this continuum mechanics comes in. And first principles of continuum mechanics are as satisfied with that condition as for the liquid itself and for the solid. Thank you. That's it for today.